Welcome to the exercises for chapter 17. This chapter is all about statistical power and sample sizes. So let's start with exercise 1. This exercise has 3 parts, and I'll keep switching back and forth between explaining the exercise and switching to code to show you my solution. So we want to start by basically reproducing this panel here. So what are we looking at here? So we have on the y-axis the statistical power. This is 1 minus beta, and basically higher numbers are in general better. And then here, what we are manipulating is the sample mean, where we're always testing as the null hypothesis of 0. So, and then we also fix the sample size to 41, and we fix the standard deviation to 2. So basically, we are holding constant the sample size and the standard deviation, and we are exploring how the statistical power is affected by the sample mean. Okay, so there's more to this exercise, but that is as far as I'm going to explain for now, and I'll switch to code and walk through my solution. Here you can see I'm fixing the standard deviation sample size, and I'm varying or setting up a vector for the sample means, which here I'm calling x bar. Okay, and then the code is actually really straightforward. I walked through the code earlier in this chapter. You can also see this in code above if you would scroll up. So basically, we just use SMP, so this is stats modeled power, dot t-test power, and dot power. So then we have to input the effect size. This is maybe a little bit confusing because sometimes when you're calculating effect sizes, you think about the mean and the standard deviation or the standard error. Here we input the effect size, which is the mean divided by the standard deviation. We, of course, also need to provide the knobs, or the number of observations. And then, of course, we also need to know the alpha, the p-value threshold for considering something to be statistically significant. As I explained earlier in this chapter, the power 1 minus beta is dependent on many factors. All of these factors. It's also dependent on the alpha threshold that you use. Okay, so pretty straightforward. What we are manipulating here is the x bar. So we just run this in a for loop and then visualize the results. So pretty straightforward in terms of code. And it is pretty interesting to see a couple things. First of all, power is always greater than 0, of course. It reflects the area under a probability density function. You can see that it's also symmetric. So it doesn't matter if the t-value is positive or negative. We can still get whatever power value we get. And that should also make sense. The sign of a t-value helps us interpret the direction of the effect, but the sign is also arbitrary. You could swap the subtraction in the numerator, and the t-value magnitude and its associated p-value would be identical. Now for the second part of this exercise, and that is to reproduce this figure here, it's panel B of the same figure. So here you see power by sample size. So now we are manipulating the sample size while fixing the standard deviation and the mean. So you can see the sample size ranges from, looks like 10 to, let me make sure I get this correct. Okay, I don't actually specify exactly what sample size you should use. So fix the mean at 0.5 and keep the standard deviation at 2, and you can vary the sample size between, I guess it looks like 10 and 250. Okay, so now I'll go back to code and show you this solution. You can see that most of the important parts of this code are the same as the previous part. In fact, I mostly just copied and pasted from the previous cell. So really, the only thing that we change is that we fix x bar, or the sample mean, and we vary the sample sizes from 10 to 250. And then, yeah, you can see all the rest of this is really the same. Here we are manipulating the number of observations. Okay, so then what you see is that power increases as a function of increasing sample size. That part is not so surprising. But what perhaps is maybe a little bit surprising, certainly important to understand, is that increases in sample size help you increase power only to some extent. Basically, the larger the sample size, the decrease in the marginal benefit of increasing sample size. So that is to say, you get a big boost in statistical power between a sample size of 10 and a sample size of 50, right? So this is a very large distance on the y-axis. So going from sample size of 10 to a sample size of 50 really increased the power a lot. But going from a sample size of 210 to 250, technically it did increase the sample size, but only by a really, really small amount. So you get this decreasing benefit of increasing sample size. This is really important to understand. This is an important concept to understand when you're doing research that is time-consuming and or expensive. So it certainly is worth your time and your budget to increase the sample size to some extent, but you're not going to get a big difference between statistical power for a sample size of 100 versus 150. So maybe if you have limited time and limited budget, limited resources, it might not be worth increasing the sample size beyond a certain point. Now for the third part of this exercise, basically here in panels A and B, we computed the power by holding constant all of the variables except for one and only varying one variable. So either the sample mean or the sample size. Now the third part is basically to combine these two to produce this image here. So what we see is power on the color axis. So white colors correspond to higher power. And then here you can see it looks like a grid. This image looks like a grid. And we get all the combinations of sample sizes and sample means that we had here. So this also is not very difficult code. You basically just take the code for these two and combine them into a double for loop. And then, then you want to just make this image. So that you see here, I'm redefining X bars and the sample sizes. Here is a double for loop. There's really no new code in this part of this exercise, except for really just the visualization stuff. So what does this image look like and what does it mean? What does it tell us? So we see, like before, the further away from zero, the null hypothesis, so the larger the sample mean, which also means the larger the effect size, the higher the power. And that's what you see here. And you can see that this also interacts with sample size. So basically having a large sample size and a large mean effect is the best way to maximize your statistical power. Now that part is kind of obvious and a little trivial, but I think it also is pretty interesting to look at this graph because in different kinds of research experiments, you might have more or less control over one or more of these factors. Of course, this is a simulation, so we can just make up whatever numbers we want. In reality, you don't get to just make up these numbers. This requires work and effort. And, the sample mean also depends on the nature of the experiment, the nature of the hypotheses, and so on. And so it is possible that you will have some experiments where it's relatively easy to get a large sample size, but the effect size is going to be small. So therefore, you will need a large sample size. But there might be other kinds of experiments. For example, if you're doing medical research on rare patient groups, then it might be very difficult and very expensive and very time-consuming to get a large sample size. So you know that you're going to be stuck with a sample size around here. So this tells you that when you are planning your research, you cannot plan to do research where the effect size is going to be small. You just won't have enough statistical power. You have to make sure that your experiment is designed so that you're looking for big effects in order to get sufficient statistical power because your sample size is fundamentally limited. That is an important take-home message that I hope you get from this exercise. Welcome to exercise 2 of chapter 17. The goal of this exercise is to basically reverse what we did in the previous exercise. So in the previous exercise, we computed statistical power by manipulating the sample size and the sample mean. And what we are going to do here is compute the required sample size in order to obtain a particular statistical power given a sample mean. Okay, so what you want to do is basically reproduce this figure here. So what are we looking at here? On the x-axis, we have the desired statistical power, and that ranges from 0.5 to 1. And then here on the y-axis, I'm plotting the effect size, which goes from -1 to +1. Now I'm computing the effect size as the mean divided by the standard deviation. Now it's up to you. You can either keep the mean fixed and vary the standard deviation, or keep the standard deviation fixed and vary the mean. It turns out that for power calculations, those two are identical. For power calculations, certainly for a t-test, it doesn't actually matter what the mean is. It doesn't matter what the standard deviation is. What matters is the ratio of the two. So that is also something that's interesting to keep in mind. The mean versus the standard deviation are important for other aspects of t-tests and interpretation and so on. But purely for statistical power, it doesn't actually matter. The only thing that matters is the ratio between these. And then what we see in the color axis here is the required sample size. So basically, this is telling us that when the effect size is smaller and the statistical power is larger, the desired statistical power is larger, we need to have a larger sample size. Okay, so a couple of other notes. What I want you to do is, okay, so actually the effect size goes to 0.95. I said 1, but it doesn't really matter. Okay, so I want you to start by fixing the sample standard deviation at 2 and vary the sample mean between -2 and +2 in 41 steps. So I know I just said it doesn't matter which one you manipulate, but to start with, set it up this way, because when you do this, you're going to get an error message. And it's insightful to see that error message and to understand what that error message means and how we can resolve it. Okay, so there's more to this exercise after this, but I'm going to pause here and switch to Python and show you the code that will get us this far in the exercise. So here you see I'm defining the means to go from -2 to +2 in 41 steps. And the required power, our requested power, is going from 0.5 to 0.95 in 27 steps, because why not 27? Okay, so then here is okay, so we have an image, so we need a double for loop. We loop over the sample, means, and the required power. And here is the formula. So this is the same function that we used in the previous exercise, but now we are using a different method. This method is solve power. To me, that sounds a little bit confusing because we're not really solving for power, we're solving for sample size. But anyway, it's just a little bit of nomenclature. So we input the effect size, we input the required power, the statistical power that we want, and of course the alpha, and this function will return the required sample size to get that level of power given this effect size. Okay, so let's run this code, and we already know that there's going to be a problem here. There's going to be an error. Okay, so the error is effect size of 0 detected. And then we see, some more information. Cannot detect an effect size of 0. Try changing your effect size. Okay, so the issue is that when you have linearly spaced numbers from minus something to plus something, there's an odd number of numbers. You're guaranteed to get exact 0 in there. I can even show you this. So we have X bars, and there is an exact 0 here. So what does this mean? Well, when we get to that part of the for loop, that value, we have an effect size of 0 divided by whatever. And so we're looking for an effect size of 0. How many subjects do you need? How much data do you need to get an effect size of 0? And the answer is unknown. You need an infinite amount of data in order to have an effect size of 0. So the formula just fails. Okay, so the solution here is very simple. We can actually just set this to be 42, for example. So now, basically, when I run this again, when you have an even number of linearly spaced numbers between minus something and plus that same thing, then there's just no way that 0 is going to be in there. So the numbers will be close to 0 in the middle of this vector, but they won't be exactly 0. Okay, so that solves one problem. There's going to be another issue, which is that the graph doesn't look like anything at all that is very interesting or interpretable. It's all black everywhere with one stripe here that goes all the way, from like gray up to white here. And this number is crazy. This is 20,000. So what's going on here? What's happening here is that the effects or the required sample sizes get so huge when the effect sizes get tiny, especially for large statistical power, we need 20,000 observations. So a solution here to address this just visually is just to specify the minimum and maximum color saturation values. So that's what I add here. And then we see this image is finally interpretable, but in here it's a little bit kind of misleading. It's a little bit hard to interpret because the values here, the numerical values here, are way, way, way above 100. They are, over 20,000. And this brings us to the next part of this exercise, which is basically to explore this huge diversity of required sample sizes by isolating individual lines from the result and plotting them. Okay, so here you can see I have just extracted the data for a couple of different effect sizes. I just sampled every fourth effect size in the matrix and then plotted for desired power and the required sample size. And what you see is these purple box lines that go way, way, way high. Above 20,000 samples are required in order to get a power above 0.9 for an effect size of 0.02. This is a tiny, tiny effect size. Okay, so let's have a look at this. Basically, this is just, it's exactly the same data as we have here, just a different way of visualizing the data. Okay, and that you see here, so I'm just plotting from this matrix of sample sizes. I'm just getting a slice from 1 to the end in steps of 5. So I think I said 4 a moment ago. It doesn't actually matter. You can also do it in 4. Okay, now here it looks like these lines are basically flat, but what's happening is that the y-axis is so highly skewed by the required sample size for a tiny, tiny effect size that it's just hard to see all these dynamics. So therefore, you can uncomment this line. So now we're only going to plot the first 5 effect sizes. So that you see here, and you can see that there is this exponential increase. So as power, our desired power increases, we need a larger and larger sample size. And of course, that depends on the effect size. So the larger the effect size, the smaller the required sample size for getting to a particular desired statistical power. Here we are with exercise 3 of chapter 17. Now, as you know from the previous couple of exercises and from reading this chapter, statistical power is a multivariable function. It depends on several factors, including sample size, the sample mean, the standard deviation, and also the statistical significance threshold. So the point of this exercise here is to explore empirically what happens when you change the alpha threshold, the statistical significance threshold. So what you want to do is copy the code from exercise 1 to create figure 7, panel A. I'm not going to scroll up because it's really just this. And remember there, what we did was fix the standard deviation, we changed the mean, and we fixed the sample size. So then we got a plot that looked like this. And now what you want to do here in this exercise is basically rerun that experiment 3 times. But each time you were just changing the alpha level or the statistical significance threshold. So here we have a threshold, a p-value threshold of 0.001, 0.01, and 0.1. And then I've also drawn a dashed horizontal line corresponding to a statistical power of 0.8, because that's just a nice reference, a typical power value. Okay, so I have a couple of remarks to make about this after I show you the code. So the coding aspect of this exercise is not super difficult because you're really just copying and pasting from exercise 1. And so you can see these 3 lines of code are basically identical, except for the alpha. And here I'm hard coding it to be 0.1, 0.01, and 0.001. And of course, that goes into different indices into this powers matrix. Now, if you like, you can also change this. I said, here, you can put the alpha values into a for loop. So these 3 lines of code, put it into a for loop by defining alpha to be 10 to some power. So that is an optional extra little fun challenge for you. Also, if you would like, you can expand on this exercise to test many different values of a statistical threshold and make an image. That's all fine and great. I encourage that, but I'm just going to leave it here for now. Okay, so what we see is basically that as we decrease the significance threshold, we increase the statistical power. So to get an effect size, a statistical power of 0.8, we don't need such a big effect size if we're willing to decrease the statistical threshold to 0.1. Now, that may seem great because you get a big effect for a smaller effect size. But of course, as you know from this book, that comes with its own disadvantage. We don't want the statistical threshold to be so lenient. Otherwise, we're going to have a larger risk of type 1 errors, which is unacceptable, right? A p-value of 0.1 is unacceptably high. 0.01 is small, 0.001 is really small. But you can see if you want to really reduce the risk of type 1 errors, you have a smaller p-value, but that comes with the disadvantage of having a reduced statistical power. So there's no free lunch with all this stuff. You always have to optimize for one thing and accept some disadvantages or some sacrifices in some other feature. Welcome to exercise 4 of chapter 17. Now, in the previous several exercises, we were setting up for loops and changing parameters to explore the impact of like the mean, the standard deviation, sample size, and so on statistical power. Now, it turns out that the stats models library also comes with built-in functions that will generate plots like what we have been creating automatically for us. Okay, so here is an example for a t-test. So SMP, so stats models power, t-test power dot plot power. And here we provide some inputs. We have the dependent variable of the number of observations. We specify 3 different levels of observations and an effect size. And so this is going to return a plot that contains multiple lines for these inputs without us having to go through and separately calculate the power in for loops and then write extra code to make plots and so on. Okay, so I'm not showing you the plot. These plots do not come from this line of code. This is just some very simple code to help you get started with this exercise. Here is the goal of this exercise. Basically, you can start from this code and modify it to create a figure that looks like this. So here we see in panel A, we are looking at the number of observations, so the sample size. And here in panel B, we have the effect size on the x-axis. And the y-axis in both cases is statistical power. And the separate lines in panel A correspond to effect size. That's what ES stands for. And here we have the sample size. So basically what we are doing is running similar experiments to what I showed in the previous several exercises, but we are adapting this code here so that stats models will compute all of these numerical values and produce these plots for us. Okay, so this is not technically part of the exercise. This is just the exact code that I showed in the book. Again, I hope this will help you get started so that you are able to complete this exercise on your own. Okay, so let's see. It is fairly straightforward. You can see we're calling this function plot power. Really, we're just changing some of the parameters in here. So here I have the dependent variable as the number of observations. So basically this is what goes on the x-axis. Here the effect size is going to go on the x-axis. I'm changing the parameters a little bit, but I do want you to appreciate that the way that we call this function is really similar. Here I input the effect size, and this is an optional input just to say which axis the plot should be drawn into. So that's really all there is to it. I think, once you see this code once or twice, you get a little bit of experience with it, you will be able to modify this code in the future. And yeah, I think the results are not actually super interesting in the sense that all of the conclusions that we would draw from these two figures is the same as the conclusions that we have been discussing over the previous several videos. Mainly, the point of this exercise is for you to understand, for you to know that this function exists, and also to understand how to use it. Welcome to exercise 5 in chapter 17. Now, in all of the previous exercises so far, we have been working with computing power for the one sample t-test, which is exactly the same as the power calculations for a paired sample t-test. But what happens if you're running an independent samples t-test? So a two samples independent t-test where you have two different groups. The calculations get much more complicated here because the two different groups can have different sample sizes, they can have different variances, and so on. And well, we are going to start exploring this function here. Previously, you have used a function called t-test power dot power or dot, whatever other method you are calling. Here, we are going to use t-test ind power. Obviously, this is for an independent samples t-test. Okay, now calling or providing the inputs into this function is a little bit weird. I don't know why the developers set it up this way. I think they could have done it in a slightly more intuitive way, but anyway, I don't mean to complain. So the way that you input the two sample sizes into this function is by providing the sample size of one group and the ratio of the sample sizes for the two groups. So for example, let's say you input that sample size the sample size of sample 1 is 20, and then you specify the ratio, which is 2. Then this function here, t-test ind power, will infer or calculate that the sample size of group 2 is 40, right? So 2 is the ratio, and based on that ratio and the sample size of one group, it infers that the sample size is 40, and so the total sample size, including both groups, is 60. I realize that's a little bit confusing. It's not my choice. That's just how it is. I hope it's understandable with that explanation. I repeat the explanation in the code. Okay, so let's see. So what you're going to do in this exercise is write a for loop that will create a plot that looks like this. So what are we looking at here? Well, let's imagine we are running different t-tests, independent two samples t-tests, and the total sample size is always 100. So that is fixed. The total sample size is always 100. The effect size is also constant for all of these simulations. I used an effect size of 0.6. Obviously, you can use whatever other values you like to explore. And what we manipulate in this experiment is the unbalanced design. So how many of these 100 samples are in group 1 and how many are in group 2? So when you have a perfectly balanced design, then it's 50-50. You have 50 samples in group 1, 50 samples in group 2. And that actually turns out to give you the maximal statistical power, which in this case is, I guess it's around 0.85 or something, 0.84. Okay, and then you will see that as you change the sample sizes to be unbalanced, remember the total sample size is exactly the same. So for this data point here, there are 20 observations in group 1, which means that there are 80 observations in group 2. Now, even though the total sample size is the same and the effect size is the same, because we have this unbalanced design, the statistical power ends up being considerably smaller compared to when it was an even design over here. Okay, so I'll have a few remarks to make about this. You're going to need to figure out how to, basically you need to find a little formula, a little mathematical formula to compute the two sample sizes and this ratio value R. But I'll show you that in a moment when I switch to code. So here, this first cell is just giving another explanation about how it works, also providing a little bit of a formula. So the number of observations in group 2 is the number of observations in group 1 times that ratio, which means that the total sample size is N1 plus N2, where N2 is defined as N1 times the ratio. I hope that's not too confusing. But as I wrote in the text, if you set up with these parameters and you get this power value, then you know that you have used this function, you have called this function correctly. Okay, so now we have our experiment. Here is the solution to the exercise. Total sample size is fixed. And then here I'm varying the sample size of group 1 from 10 to 90 in steps of 5. And let's see, so here I'm using the function. Remember, the effect size is fixed for all of the runs, all of the iterations through this for loop. And then we have the number of observations and the ratio. We're also keeping the alpha threshold fixed here. So it's not too difficult to calculate the sample size ratio. Here I'm calling it SR. So we know that the sample size of group 2 is the total sample size minus the size of group 1, and then we can just compute that ratio. So that ends up being SR. Okay, so now we see the results. Once you figure out, I think this is the only tricky part to this exercise. Everything else is pretty straightforward, I think. So I find this result to be very striking because it means that even when fixing the effect size, we still see that having an unbalanced design really negatively impacts your statistical results. Going down, I mean, this is a little bit extreme to have a sample size of 10 versus 90 in the two samples, but still the statistical power goes down to around 0.4, is a little bit above 0.4 versus a bit above 0.8. That is a really striking difference. This is something that you would write grant proposals to propose research where the sample size is this big. If you would write a grant proposal and you would say, give me money to do research to get a sample size of this size, your funding agency would say, no, that's insufficient statistical power. And it's really, in this case, entirely due to the unbalanced design. So that really has an impact. So once you understand this code, once you have this code working, I encourage you to continue exploring. You can see what happens as you change the total sample size. So maybe set the total sample size to be, 500 instead of 100, and obviously change these values as well. You can also try changing the effect size. Actually, we can do that here. So here, let's make the effect size, how about 0.96? So now we have a larger effect size. And the interesting thing is that the overall shape of the statistical power response is comparable to the previous one in the sense that we get this inverted U effect where having an unbalanced design lowers the statistical power. But in this case, the power doesn't really drop that severely. So, I mean, this is amazingly high power, right? It's almost 1. But, even going down to this really unbalanced design where we have 10 subjects in one group and 90 subjects in the other group, that only decreases the power down to about 0.8. So that is, again, quite an acceptable level of power. And what changed is the effect size got much bigger. So now, let's try with an effect size 0.36. So now the effect size is really small. And now this is really unacceptably low. I mean, even this is really very low power. Welcome to exercise 6 of chapter 17. This exercise is all about using empirical simulations to confirm the theoretical power calculations. Now, this exercise and also the next 2 exercises are all closely related to each other. So if possible, I recommend putting aside a block of time so you can work through these 3 exercises in one sitting. I think that will really benefit your understanding of how to use empirical simulations for power calculations, and also what to do, how to calculate power when your data violate the assumptions of power calculations. Okay, so anyway, what we are going to do here is run a bunch of t-tests on simulated data sets to determine whether the empirical statistical power corresponds to the theoretical, the analytical power that we get from applying formulas and algorithms. Okay, so here's what you want to do. Start by simulating data as 38 numbers drawn from a Gaussian distribution, a normal distribution with a population mean, so an expected population mean of 0.8 and an expected population standard deviation of 1.8. Okay, and then you want to, so you draw that random sample and then apply a t-test to test against the null hypothesis that mu equals 0. Now, we know that this null hypothesis is false. We know exactly the population characteristics here. But, the difference between the population characteristic and the null hypothesis is relatively small compared to a standard deviation. It's like half a standard deviation. So we are not guaranteed to be able to successfully reject the null hypothesis in every single sample, even though we know that the true state of the world is that the right thing to do is to reject the null hypothesis. So repeat this simulation 10,000 times. That's what I say down here. So 10,000 times, and each of those each of those experiment runs, you generate new random data, same population characteristics, same null hypothesis to test against, and you want to count how many of those 10,000 data sets, those 10,000 samples, had a t-value that allowed us to reject the null hypothesis. Again, that's the right thing to do. We want to reject the null hypothesis. And then you also compute the theoretical power using stats models library. And then you can print out both. So you can see, based on the known population mean and standard deviation and the alpha threshold of 0.05, the theoretical analytical power is 76%, so 0.76. And then from the empirical simulations, we got 76.07. That's really, really insanely close. That's remarkably close correspondence between an analytic result and an empirical confirmation of that result. Okay, so once you have the code set up, then I encourage you to spend a few moments just playing around with the different parameters. Change the sample size, change the standard deviation, change the mean, and so on. And basically, you should always find, maybe some exceptions if you have ridiculously, if you have a sample size of 2, you're going to get some weird things. But for any reasonable value of these parameters, you should get a really close match between the analytic formula for statistical power and the empirical result of post hoc power. So here I define the population parameters here and the sample size over here. Here I'm defining the critical t-value. So remember that to reject the null hypothesis, the observed t-value needs to be more extreme to the left of the critical value or more extreme to the right of the critical value. And of course, this is a two-tailed test. So we obtain the critical t-values as 0.25% on the left and 97.5% or 0.975 on the right side of the distribution with this degrees of freedom. Okay, here's the number of simulations that we're running, and this is a counter, basically. So every time we reject the null hypothesis in a sample, I'm going to add 1 to this. And then we just divide this by this to get the proportion of times that the null hypothesis was rejected. Okay, so here's our experiment. Loop through our 10,000 simulations, drawing a new random sample with these population characteristics. Of course, the sample mean and standard deviation is not necessarily going to be mu and sigma, although we do expect them to be reasonably close. Okay, so yeah, here I'm computing the sample mean, the sample standard error, because we need that for the t-value. So here I'm computing the t-value. And then it's pretty straightforward. We just say if the t-value is less than the critical t-value on the left side of the distribution, or if it's greater than the critical t-value on the right side of the distribution, that means we reject the null hypothesis. We consider this result to be statistically significantly different from the null hypothesis value of 0. And of course, if you're testing against any other null hypothesis value, that would be in here like this, but that's not what we're doing here. But implicitly, you can subtract 0. Okay, so now our empirical estimate of statistical power is the number or the proportion of times that we rejected the null hypothesis, and I'm multiplying it by 100 to get 2%. Okay, and then here I'm computing the analytic power using the SMP, so stats models power library.ttest power. Okay, so this code you've seen before. And then I just print out the results. And we see, okay, so this is a little bit more different from what I showed in the text, in the book, but still really, really close, remarkably close, considering that this comes from a formula and this comes from just a bunch of simulations. This code cell here is exactly the same as this code cell, or the result is exactly the same. It's just that up here, I just wrote out a lot of extra code because I really want you to understand the concept of rejecting the null hypothesis based on the relative position of the observed t-value to the critical t-values. All that said, in practice, you can just use this. That's so you can see here I'm generating a random sample, inputting that sample directly into the t-test function, and then just saying, well, if the p-value is less than 0.05, that is exactly the same thing as saying if the t-value was more extreme than the critical t-values. So I hope that makes sense. Basically, this code cell and this code cell have the same result. Here I wrote out the procedure in a little bit more detail because I hope that helps you understand what power really means. It literally just means how likely are we to reject the null hypothesis. Okay, so then, yeah, we can run this here. Again, although this doesn't give us any qualitatively different results. So I am going to stop the video here, but as I mentioned a few moments ago, I do encourage you to experiment around with this code and try changing some of these parameters here and running it again. You don't have to do this very systematically. Basically, you just want to see that as you poke around in this parameter space, you basically always get a really good correspondence between theoretical and empirical or simulated power. Here we are in exercise 7 of chapter 17. This exercise follows super duper closely from the previous exercise, so definitely make sure you've done exercise 6 before working through this one. And then also as a reminder here, if in the previous exercise you change the parameters around from what I specified in the beginning of the exercise explanation, then please go and change them back to their original values. That will help make sure that you can qualitatively obtain the same result that I am going to get in this exercise, exercise 7. Okay, so basically, yeah, the empirical and analytical power matched super closely, and that's largely because the data were perfectly consistent with the assumptions of a t-test and therefore also with the assumptions of statistical power calculations. What we're going to do now is break the rules and see what happens. Okay, so start by copying the code from the previous exercise, but you just want to change how the data are simulated. So instead of simulating the data as a normal distribution or drawing the data from a normal distribution, you want log normal distributed data. And it's really simple to do that. Very little, tiny change in the code. Basically, in the previous exercise, you were computing the data x, and now you just say e to the x. So now the data that you will use for this exercise is y equals e to the x, where x is the same data with the same parameters, same sample size, and so on, as with the previous exercise. Now, when you're computing the analytical statistical power, you need to know the theoretical population mean and the theoretical population standard deviation. Those are not the same thing as 0.8 and 1.8, which we specified in the previous exercise. And that's because, as you learned in chapter 5, when you have a log normal distribution, the mean and the variance combine and they get pushed through the natural exponential function. So this is actually just a reminder of what you learned in chapter 5. It's just reprinted here to make it easy for you. Okay, so when computing analytical statistical power, use these equations. The population expected mean is, I call this mu tilde here, and it's e to the mu, so where this is 0.8, and sigma squared, and sigma is 1.8. These are the parameters from the previous exercise. And then, yeah, here's the population value for sigma. Okay, so I'm going to discuss what the outcome is going to be and why the outcome makes no sense whatsoever. But first, I will show you the code. So here we are with the code. Now, almost all of this code is identical to the code from the previous exercise. There's just a couple of things that I changed. So I added this. So I literally just took, this was already there before the previous exercise, and I just pushed those random numbers through this natural exponential. Everything else is the same. All this stuff is the same. So this is the same. This is also the same. This is the same. And then, I've just added here the calculation of the expected population mean and standard deviation. And this is just the translation of those formulas into code. Okay, so let's run this. And you already know that something weird is going to happen here. And what happens is we get ridiculous results that make zero sense. There's two reasons why these results don't make any sense. First of all, the theoretical and empirical or simulated power are way different. I mean, the empirical power is like 4 times higher than the theoretical power. So that's already weird because in the previous exercise, we saw that these two quantities matched really, really closely to each other. But but there's an even deeper problem, a much, much bigger problem, which is that neither of these results make any sense whatsoever. And to demonstrate why these don't make any sense, let's plot these data. So the data value variable is called sample, and we can just say plot sample like this. It's only 38 data points, so we don't really need to make such a big, we don't need to make like a histogram or anything. Notice there's no negative values. This is e to the a bunch of numbers, including negative numbers, but e to the anything is going to be a strictly positive number. And yet the alternative hypothesis, or the null, sorry, excuse me, the null hypothesis that we are testing against here is 0, that the mean of these data equals 0. How can you possibly, the results should always be wildly statistically significant here. Why do we get a power less than 100%? Well, the answer is that we are violating the assumptions of the t-test and also violating the assumptions of the statistical power calculation. So basically the violations of the assumptions are sufficiently horrendous that neither of these results can be trusted at all. And that leads us to the solution, which is going to come up in the next exercise. Here we are in chapter 17, exercise 8. This exercise follows super duper closely from the previous 2 exercises. Now, in the previous exercise, we got this nonsensical result of statistical power. And I claimed that that was because our data violated the assumptions of the t-test and therefore also of the power calculation. So what we're going to do in this exercise is copy the code from the previous exercise and make 2 modifications. The first modification is you want to use the Wilcoxon test instead of the t-test. Remember from the chapter on t-tests that the Wilcoxon test is a non-parametric alternative. It evaluates the median of a data set, and it doesn't matter what the distribution characteristics of that data set are. So use the Wilcoxon test instead of the t-test. And the other modification from the code from the previous chapter is to basically just get rid of the analytic power. We already know that that is going to give us nonsensical, non-interpretable results. So just get rid of it. We don't care about it anymore. Okay, so that is the first part of this exercise, and I'll show you the code in a moment, but basically you should find that the statistical power goes to 100%. And I'm going to talk again about why that needs the power. Any valid interpretable power analysis needs to be exactly 100% in this simulation. Okay, once you've confirmed that that works empirically, then what you want to do is basically just modify the code a little bit to include a null hypothesis value. This is just a minor change from the code. And basically you can test against the null hypothesis value that the data were drawn from a sample with a median of 10. So that's your null hypothesis value. In fact, the population expected median is 11.245. So there really is a difference between the true population parameter and the null hypothesis value. And you should find that the power is going to be somewhere around 0.8 for this test, given all of these parameters. If you are fresh out of exercise 6 and 7, then you will recognize all of this code. It is literally copied and pasted. All I did was change this. So I'm using scipy.stats.wilcoxon instead of using the t-test. The way I simulate the data is identical. All this stuff is identical. This stuff is identical. And yeah, we don't get, there's no analytic power here to compute. We are only going to compute the empirical power. We find in this experiment that the empirical power from these simulated data is 100%. Literally, every single time that we simulated the data, we got a statistically significant outcome of the Wilcoxon test, which means every single time we rejected the null hypothesis. Now, why does it have to be that result? Why can we not trust any result other than 100%? Because here we still are testing against the null hypothesis that the data were drawn from a population with a median of 0. Implicitly, there is a -0 in here, and that's our null hypothesis value. And remember, because these data are strictly positive, there's literally it's impossible for there to be a negative number in here, which means that testing against the median of 0, obviously, the most of the data will be above 0. All the data are above 0. So if you don't get 100%, then you made a coding error somewhere. It couldn't work out any other way. Okay, so then the last thing that we want to do in this exercise here is to basically just adjust the code. It's a really, really tiny adjustment. Probably don't even need to have this entire new cell of code here. I could have just written this into it. But anyway, so tiny adjustment just to add a more reasonable null hypothesis value. And here I'm going to use 10. So let me plot the data again. So plt.plot sample. Fix this typo here. Okay, so here you see this is an example of sample data, and here is our null hypothesis value of 10. And now this is much more reasonable than a null hypothesis value of 0, which is ridiculous. So we're testing against the null hypothesis of 0, and we do expect that that should be rejected most of the time. You can see, there's clearly more data, at least in this particular sample. There's clearly more data below 10 than there is above 10. And indeed, we find that the empirical power from this simulation is 80%, or in other words, 0.8. So this is certainly a much more reasonable value. And what's the conclusion from this exercise and the previous exercise? The conclusion is that power calculations are great. You should definitely use them, especially to estimate a required sample size given a requested power. But that is just not always feasible. It's only possible to do if you have data that conform to the assumptions of parametric statistics and also power calculations and sample size calculations. If your data violate those assumptions, or if you are planning a study and need to calculate the sample size that violates those assumptions, then you have to simulate data. That's the best alternative when you cannot use the analytic power calculations. And the way to do that, the way to get the empirical power calculation, is by simulating data that have the characteristics that you expect in the data that you will collect. And then you can do something like this. And then basically to invert this, to compute the required sample size, what you would have to do is an iterative approach where you would basically take all of this code and put it inside another for loop that varies over sample size, that manipulates sample size. So then you would get an empirical simulated power for each sample size, and then you can figure out what is the sample size that gives you, for example, 90% power. Welcome to exercise 9 of chapter 17. In this exercise and also the next 2 exercises, we are going to compute post hoc statistical power, also sometimes called achieved statistical power, in a real data set. This is the wine quality data set that we've worked with several times before. For example, in the chapter on t-tests, that's going to be in this exercise. And then the next 2 exercises, we are going to explore the required sample size for a given level of power in those same data. Okay, so let's begin with exercise 9. So what you want to do is start by importing the wine quality data set. Now, we've worked with this before, as I mentioned. This is a reference to an exercise in the chapter on t-tests. You can look it up. Basically, just copy a bunch of code that you already have, or copy my code from online to import the data. Don't worry about processing or cleaning the data. You don't have to worry about anything to do with the data except for making a new column in the data frame that corresponds to the Boolean value of wine quality rating. So we want wines to be rated as low quality or high quality, and we are going to use that to split the data into 2 independent groups to perform a t-test on the different chemical variables that we have in this data set to see which of these variables significantly distinguishes low quality from high quality wines. Now, you have already computed independent samples t-tests on these data in the chapter on t-tests. So feel free to go back to that chapter and copy as much of that code as you like. Or if you want a little bit of an extra challenge, then you can write everything here from scratch. Okay, but basically the important point of this exercise is to produce a output that looks like this. So for each variable, this is each of the features that we have in the data set, you compute and report the t statistic, here's the degrees of freedom, and the p-value corresponding to this t-value, and then the achieved statistical power using the methods that you have learned in previous exercises earlier in this chapter. Now, one thing to keep in mind is that because we are performing so many tests and all these tests are independent of each other, then make sure that the p-value threshold that you want to use is not 0.05. That is not an appropriate p-value threshold or alpha level for this experiment because we have so many variables that we are testing. So make sure you use a Bonferroni corrected p-value significance threshold. Okay, and then you should be able to reproduce all of these numbers here. I have a couple of remarks to make about these levels of power, and I will say more about this after I show you the code. Okay, so here I'm importing the data. These are the columns that we want to perform a t-test on, and here I create a new column for the Boolean quality variable. Again, there's nothing new in this code that you haven't seen before. It's all copied from the, looks like exercise 12 in the chapter on t-tests. Now, previously, when we worked with these data, we also applied some transformations. We did some cleaning, some z-score based cleaning and data removal. If you want to do that here, that's fine as well. By all means, go for it. Obviously, in real data, that is something you would want to do. But for the purposes of this chapter, we don't really care about that stuff. We just care about making sure that you know how to compute the achieved power and the necessary sample size for a given power, which we will explore in the next exercises. Okay, so here is the alpha threshold. It's 0.05 divided by the length of this variable, columns to test, which is basically all the columns that we will use as the dependent variables. So all the number of tests that we will perform here. Okay, so then we loop over the different columns. Here, this is just for convenience. I'm extracting the high ratings and the low ratings. So this is the data for this column only for the rows where quality is true, meaning high quality ratings. And here, this is only for the quality ratings that are false. So these are the two samples that we will use in the t-test. Here, this is the sample sizes of the two groups and their ratio. This we need for computing the statistical power, as you saw in the previous exercises. Okay, so we need to compute the effect size. Now, the effect size for a one sample t-test is very simple. It's just the differences of the means of the two paired tests, or the mean of the one sample minus the null hypothesis value in the numerator, and then the denominator is just the standard deviation. It's that simple. But as you know from the chapter on t-tests, computing the effect size of a two-sample independent samples t-test is not quite so straightforward. So there's a little bit more stuff that we need to go through. If you're confused by this formula, it's essentially looking at the variance. So it's the summed variance for the high data set and the low data set. It's scaled by the sample size, and then essentially we're averaging those two together. So like a weighted average, weighted according to their sample sizes. And then we take the square root to give us our estimate of the pooled standard deviation across these two samples. Again, if this is completely unknown and confusing, then you might want to refresh your knowledge of the chapter on t-tests. Okay, here is where we compute the post hoc power, or the achieved statistical power. So you have seen exactly this function before. There's really no difference from how we used it before, just that all of these parameters actually come from real data instead of from numbers that we just generated to make a simulation. Okay, so that is statistical power. Here I compute the independent samples t-test on these two. And here I'm just saying, we have so many comparisons to do here. I'm not going to go through each one to test whether we can assume equal or unequal variance. I'm just going to keep things simple and straightforward and assume unequal variance in all cases. Okay, and then the rest of this is just printing out the variable name, the t-value, and the degrees of freedom, and so on. So what do we make of these results? Well, it's pretty interesting to see that in most of these cases, the power is either extremely high or extremely low. There's a few intermediate values like here, I guess around 0.9, but most of the power values are close to 1 or they're close to 0. In the cases where they're close to 0 was where the p-value was close to 1. So here and here, the t-value is also very close to 0. Now, we have degrees of freedom of basically 1,600, almost 1,600. So that means that these sample sizes are ginormous. And that means that if you have such a huge sample size and the t-value is so close to 0, formally, we cannot say that we have proven the null hypothesis. All we can say formally, really statistically, is we cannot reject the null hypothesis. But sometimes you have samples that are so big and the effect size is so tiny, t-value is just so close to 0. We can colloquially say that this is very strong evidence for the null hypothesis. Again, that's just a colloquial interpretation, but there's really no effect in this data set of residual sugar on ratings of wine quality. So that's why the power is so low, because there's really nothing here to find. On the other hand, these effects are huge. They're, the t-value is really big. The p-value, who knows what the actual p-value is, because I clipped it off here. But it's certainly much, 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 much smaller than 0.0001. And you can also see this with the really large degrees of freedom. So because we basically have, 1,600 samples. Now, this leads to an interesting question. Let's say you wanted to reproduce these findings or perform another study that is kind of comparable. Maybe you're looking at, red wines versus white wines or wines from different regions, but, you don't have the resources or the budget to find 1,600 people and give them all a bunch of wines to rate. So you might look at these data, these published data, and say, well, based on what they have found here, I want to figure out what is the approximate sample size that I would need if I can expect I'll perform similar analyses. I expect similar magnitudes of effects, so similar effect sizes, but I want to have the smallest sample size that I can get away with while having a power that is still acceptable. And let's say acceptable, we would indicate as 0.8. So that is not what this analysis tells you. This analysis tells you the achieved post hoc power for the sample size that we already have. So if you want to basically turn this analysis around and say, what sample size do we need given a desired power, then that's a different analysis. And that is the goal of the next exercise. So I'll see you then. Here is the video for exercise 10 of chapter 17. This exercise follows directly from the previous exercise, so make sure you've done that one before doing this one. Okay, so as I mentioned at the end of the previous video, what we want to do here is determine the minimum sample size that would be required to obtain a statistical power of 0.8 or 80%, given the observed effect sizes and the p-value threshold and so on, basically using all the data that we have from the previous exercise, which is a real data set. So again, the idea is that, maybe we want to conduct a follow-up research experiment, but we don't want to get 1,600 participants. So how many participants do we actually need? Okay, so I haven't yet shown you code to compute the required sample size for 2 samples t-test, but basically the idea is you use this function, so SMP, this is stats models power, dot t-test ind power, obviously this is for an independent samples t-test, dot solve power. So this is the function that you want. And the idea, the way that you use this function is you provide all of these inputs and you set one of them to be none. And the output of the function is going to be whatever you defined none to be. So we want a power of 0.8. We have an effect size of 1, alpha 0.05. Obviously, you're going to use different values in this exercise. I'm just showing you some template code so you know how to use this function. So now this function will return the ratio. So let's say it's a 0.2, approximately 0.2. But, when you're computing required sample sizes, you always want to round up for reasons that I explained towards the end of this chapter. There's a number of reasons for that, but the main one is you might have to throw out some data because of noise or technical equipment. So it's always better to overestimate the sample size than underestimate the sample size. Okay, anyway, so with a ratio of 0.2, the sample size for group 2 would need to be 0.2 times 50, which is about 10 observations. Okay, given this effect size and this alpha threshold and so on. Or here's another example. So now this is exactly the same as this line of code here, except that now I've specified the ratio to be 1. Here it was none. And then I've left this. So knobs 1, n observations in group 1. I set that to be none, whereas here I set it to be 50. So again, the principle, the concept is that you specify n minus 1 of these variables, these input options, and you leave 1 to be a value of none, and that's the one that gets returned. Okay, so in this case, the function returns 17, which means that you need 17 in each group. And because I've specified ratio equals 1, then the two groups will have equal sample sizes. Okay, so that's just background for how to implement this exercise. Okay, so now the idea is fairly straightforward. Basically, you go back to, you want to copy and paste as much of the code from the previous exercise as you can here. So we already have the t-statistic, we already have the sample sizes and so on. So basically, you just want to compute, we have the power that we want, which is 0.8. And then what you have to compute is the required sample size. You want to keep the sample size of the high quality condition as is and compute the required sample size of the low quality ratings group. So in other words, it's going, the code is going to look similar to this, where you specify the number of observations in one group and you ask stats models to return this ratio value, which you would then multiply by this number, round up, and that gives you the required sample size for group 2, which is the low quality rating. Okay, I hope that makes sense. Now, you're going to run into some errors. There's going to be some problems, and I'll show you what those are and what they mean. But basically, you're going to have to add a little bit of code to deal with situations like that. So what I did was report this. So I should just say does not compute anytime that the power calculation failed miserably. It crashed and burned. And so in that case, I just printed out this message. Otherwise, it prints out the required sample size here. The first code cell here for exercise 10 is not super interesting. This is just copy pasted from the code that I showed in the book. That's in case you want to run it. You don't need to type the whole thing out from how it's printed in the book. Otherwise, yeah, this is just to show you how to use this function and this method. We don't actually need these for the exercise. Okay, so obviously you will recognize a lot of this code here. It's nearly identical to the code from the previous exercise. So here's our p-value threshold, extracting the data for each column. So we're looping over all the columns, all the data features, the sample size and the ratio, the effect size, all exactly the same. Okay, so here is what's new. Here I say power dot solve power, and then I provide the empirical effect size that we got from this data set, the alpha threshold, which is the Bonferroni corrected threshold, the requested level of power, statistical power, so 0.8, and the number of observations in the high quality group. And then here for ratio, I say none. So this is what Python will return. So now this is going to crash on some cases, and maybe I will, let me do this. gonna delete this and comment out this just so you can see what the error message actually is. So run this code here, and you see we get an error message. And unfortunately, this error message is not really very insightful, which is to say, you don't really see exactly what the problem is just by looking at this error message. This is an unfortunate feature of Python, that the error messages are occasionally very useful and informative, but very often not. But what is interesting and what is actually very insightful is that you see that it actually did print out for the first 3 columns. So what this tells us is that there isn't a problem with the code per se. You know, if we did something like this, you know, if we didn't get any output at all, here we don't get any output, then we know that there's something wrong with the actual code. In this case, it's just a typo. But the fact that we do get valid outputs, valid computations for the first 3 rows up to citric acid, so, you know, it's going up to here, that tells us that the problem actually happened on this line where the power was very small. Okay, so let me put back all of this stuff here. Okay, so that's why I have this try and except statement. So basically, it's going to do this, except if this line of code produces an error, in which case it will go to this exception and it will print out the variable name and does not compute like a good little robot. Okay, so here we see the required sample sizes for these 2 effects, or for these 2 different groups. And you can see that it varies quite a bit, right? So it varies like an order of magnitude, or a little over an order of magnitude. And that's really because when there's a huge effect in the data, you do not need a lot of observations to show that there is a strong effect. But the smaller the effect size, the more data you need, the larger the sample size needs to be. That's basically what's going on in these cases. The effect size is so small because there's really no effect. As I discussed at the end of the previous video, there's no effect. This effect is so tiny, the t-value is so tiny that if there really were an effect, that effect would be so incredibly tiny that the sample size would need to be absolutely ginormous. It would have to be huge. That is something that we are going to continue exploring in the next exercise. Here we are in exercise 11 of chapter 17. This exercise is just a little bit, just a minor modification from the previous exercise. So remember, in the previous exercise, exercise 10, we computed the required sample size for group 2, so the low quality ratings group, based on a desired statistical power of 0.8 and the observed effect size and so on. So what you want to do here is just copy and paste the code from the previous exercise. And what you want to do is, instead of fixing the sample size of the high quality wines, you want to fix the sample size ratio and then compute the required sample size. And this ratio, you're not going to set to 1 so that we have perfectly balanced groups. Instead, you set the ratio to be the observed ratio, so the actual ratio. So you can see that the sample sizes for the 2 groups are not going to be the same. Now, why do you want to do that? Or why do I say to do that instead of just setting the sample size ratio to be 1, to force equally sized groups? Well, the reason is that this is not an experiment where we can manipulate which individuals, which wine tasting experts go into which category. And that's because, you know, the way this experiment worked is that people drink the wine, they taste the wine, and then they make a subjective judgment. Do they say this is a low quality wine or high quality wine? We cannot force people to say how many wines are high and low quality. So instead, we just have to assume that the ratio, the approximate ratio of the 2 groups will be the same in future samples. That's an assumption. You can set this up in many very different ways. You could set up the experiment in different ways to force the number of high and low quality wines to be the same. Lots of ways you can do this exercise in the real world if you were really doing something like this. But for now, for this exercise, set the observed ratio for each variable, the sample size ratio that you input into the power calculation function set that to be the observed ratio of the sample sizes based on the data set that we are working with. So I hope that makes sense. And then you want to, again, print out a table that looks like this. So we see for each column, each variable, each feature of the data of the wine, we have the number of subjects in the high rating and the number of subjects in the low rating group. Okay, and again, this is to achieve a statistical power of 0.8 or 80%. I have several remarks about this outcome, and I'm going to discuss those when I show you the code. Again, you will recognize this code. It should look familiar. All this code, all of this stuff certainly is literally exactly the same as in the previous exercise. This line of code is nearly identical. This part is the same. A lot of these parameters are the same. The only difference is that in the previous exercise, we defined this and we set this to none, and now we are defining the ratio and we are setting the number of observations to be none. So the ratio is determined by the empirical ratio of these two sample sizes. And then we print out the results. In this case, it turns out we don't actually need this because all of these examples can be computed exactly. Okay, so let's have a look at these hilarious and insightful results. What do we see here? Well, we can see that the required sample size for for a statistical power of 0.8 varies quite a lot. So the amount of alcohol is we need very, very few, relatively few observations in these two groups. And that should make sense. I think the more alcohol there is in the wine, the more people enjoy the wine. Seems pretty believable to me. Here we have fixed acidity. This is a smaller effect size. The effect size is not as big. So here we need, a total of like 1,500 wine tasters in our data set, in our experiment, compared with just 60 here. And then we have this, which is absolutely hilarious. Residual sugar. We need basically almost 3 million people. That's like the entire population of many cities in the world. So get every single person in the city. And you couldn't even do this study with everyone because, there's a lot of kids. You can't force them to drink wine. So it would be, a really large sample that you would need. And why, what do we make of this? Again, this was the variable that had a high degrees of freedom, but extremely small t-value, very close to 0, and a very large p-value. And so this, and also the pH of the wine, basically, what we can colloquially interpret is that there is no effect of sugar on ratings of wine quality. And so, we do this calculation assuming that there is an effect to find. We just need enough data to find it. And so you need like 3 million people because the effect size is so tiny. But that effect size is really just due to noise. There's nothing there. Okay. Now, it's one of the interesting things I would like to remark about this is that when you're doing power and sample size calculations for real, like in a research proposal or in a grant proposal or in an ethics approval to get approval to conduct some research on humans, for example, then you will get these kinds of results, and they are difficult to know what to do with because it's all the same data set, right? These all come from the same data. It's the same participants. These are just different chemical properties of the wines. And yet the required sample sizes are very different. So what do you do when you have different analyses in your proposed research that have very different required sample sizes? I mean, the easy thing to do is to go with the biggest one, or at least, the largest sample size that you care about. We're not going to consider this. But, there might be time restrictions or financial budget restrictions that would prevent you from collecting, 3,500 data points because, that's just a lot of people to get. So maybe, you have to find some balance and you say, well, we're going to take the middle ground and go for 500. And what we have to accept is that some of the findings will have a very large statistical power, and some of the findings will have a small statistical power. And, it's very easy for us just sitting here learning about statistics to say, no, 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 you should always do the right thing and maximize power. But when it comes down to it in the real world, it can be very difficult and very expensive, and very time consuming to collect really large data sets. So, when the rubber hits the road, there's got to be some sacrifices and some decisions to make about how to get research done in practice versus what you want to do in theory.